second presentation will be presenting and visualizing instrumented vehicle data using open source tools. Will be presented by Marcelo Simas from Westat.
Okay. So I work in the Atlanta office of Westat. We used to be a separate company. We were acquired by Westat about 5 years ago. But we have a group of people that develops tools, processes data, and does support for travel surveys and other transportation studies at Westat. What I'm going to talk about today is something that we worked on a year and a half ago or so, which was instrumentation package and then the data processing visualization that came out of it to support driving studies. So these driving studies are studies where you invite participants to drive vehicles that you have instrumented. And the vehicles have cameras, and you typically try to record data from the engine and from other parameters in the car that you connect to the car to get at. And then you have other sensors like GPS, accelerometers, and whatnot. And what people are trying to look at is driver behavior. And for this specific study, it was seatbelt usage. So they were really very interested about, people were buckling up. When were they buckling up? If they were not, would they do it at some point later in the trip? And did it change over time? We monitored the driver for 1 week. And I say monitor, but really it was recording the data and then looking at the data after the fact. So it was instrumented for a week. And then they would be able to bring back the vehicle. So we developed this system called WesDAS. That stands for Data Acquisition System. The guys in Rockville here, the main office is in Rockville, Maryland, were the ones that had instrumented vehicles before and have done this type of stuff, but they wanted to move away from the PC platform. They had developed something that ran on a box that was a PC in the trunk of the car, and they wanted to see if we could make use of some of the newer devices that are out there. So as I said, some of the challenges that we're going to talk about is how we took the data out and processed it and visualized. So 2015 is when this whole thing got started, and we decided to build something that was using Android phones. If you think about it, these phones have batteries, GPS, accelerometer, gyroscope, temperature sensor for the battery. It has a microphone, so you can record audio, or you can just measure the noise level in the cabin. And then it has a camera, so you can actually mount it in a way, take pictures, and record video with the whole thing. So we thought, sounds like a great idea, let's try to do it. So the result was this thing called WesDAS that runs on Android. But once the data was collected, we realized we had to merge it all together. And the challenge is you have all these sensors and they're reporting data at different frequencies. Some is 1 per second, some is 10 per second, some is just once in a while. And we're also getting data from the vehicle, which has a different problem altogether. Come on. So as I said, there are multiple sensors that we can get straight out of the phone. But we're also connecting to the OBD port in the vehicle to get the CAN messages that are logged by the vehicle. These vehicles nowadays, they have a data bus that all the electronic components talk to each other, including the engine, and all the stuff that you press has recorded in that. And if you know the right messages to listen to, you can decode a lot of what's happening in the vehicle. So we use that to extract the seatbelt state, buckle and unbuckle of the front seat passengers, headlights, a gear position, the speedometer values, the speed that's being sensed by the vehicle, and ignition position. So if it's off and just initial state and then started. And there's lots of other things that you can extract from that data, but the messages are infrequent. They don't happen all the time, and they come at irregular time intervals if you think about it. We also have recorded embedded in the OBD data markers for pictures and videos, so that we can record in the data stream when we took a picture in the vehicle, or when we start recording a video and ended recording a video, because you want to go back and time sync all this stuff. We started using the video camera in the phone, but what we learned is that these phones don't like to get hot. And guess what? Cars get very hot. So initially the phone was mounted on the top of the cabin, right behind or right in front of the rear view mirror, pointing downwards, like I showed on that picture. You could see the person sitting down and the buckles in the car. That was the whole idea. But in the summer, they got so hot that the phones would automatically shut down. These phones, because they have a big lithium-ion battery, once the temperature crosses a certain threshold, they stop charging, and then if it gets a little hotter, it just gets killed altogether, and it does not come back. It's not like, okay, it's going to be off, and then once it cools off, it just dies. So we ended up having to move the instrumentation a little bit to a different setup. So as I said, we had an Android phone. We're using an Arduino, which is a microcontroller board that is programmable, and you can hook up different sensors to it. And we're using a Shield, which is just an accessory board that plugs into the Arduino to connect to the OBD port in the vehicle to get the data. So that's the main data acquisition system for getting the data from the vehicle. And we're using a Raspberry Pi for the camera because we couldn't use the phone camera. Because the phone was getting so hot, we had to move it under the driver's seat. And we have a separate Raspberry Pi that basically we talk to through the Arduino to take the pictures, record the video. And the Raspberry Pi is like a mini Linux or Unix computer. And you can put in an SD card on it, and it's got gigabytes of storage, so you can record quite a bit of video on it. We record 30-second clips of every time that the person opens the driver door, so we can get the seat belt timing or look at what they do. Some people buckle the seat belt and sit on top of it. So we want to see that. So that's the whole reason why we're taking pictures and recording the video. And we keep extending that video recording every time the door opens again. So that is the final instrumentation that we ended up putting together for that. Just to give you an idea, lots of little things, lots of wires, and you have to all install that in the car and provide power to it. And have it so that it's not visible, because you don't want people to be reminded all the time that they're being monitored. So the cables all get tucked away and the camera's painted black and it's mounted up on the top, and ideally within a few hours people forget that they're being measured and monitored. So as I said, the CAM messages, it's the data from the OBD sensor. The way that the data bus works is it sends these messages out, and each message has a header that tells you what type of data is in it, and it's got a payload of 8 bytes. And we just take that data, record it all, and the WesDAS application running on the phone uses a little SQLite database that basically logs everything. So whatever frequency the data comes in, we just keep logging it, and we log the raw bytes in the table there. The nice thing about SQLite is that you can then take those bytes that are logged and combine them to make up higher resolution numbers. So the speedometer comes in as like 2 bytes, and you combine the 2 bytes using a bitwise operator and then some scaling factor, and then you can get that number out. Initially, we were taking that data, from the multiple sensors and the OBD messages being filtered out, and try to combine it all into a single analysis file. That's what people that look at the data want to have. They want to have a single wide file with a column for each variable, and then there's time going down. And we were doing that with just straight SQL running on SQLite, and it just took forever. It just would not end in a reasonable amount of time. And I said, okay, let's break this up. Let's do like multiple SQLite databases, put just 2 bits of data on each one of them and run them all in parallel. We have these computers now with 4 cores, 8 cores. I mean, it's got to go fast, right? Well, it still took multiple minutes to get that done. And in the meantime, I kept getting requests from the person that was actually deploying instrumentation and then looking at the data and say, why don't we just combine this all in the field? And I'm like, no, let's keep the data in the original form so we can always resample it and look at it different ways. And that's when I started to look around in R to see if there was something that could do that. And I'm like, it's been done. So there's all these packages already that exist. They're designed exactly for this purpose, to take time series data that is reported at irregular intervals and then combine it all, and it does it in memory, and it does it in a very fast way. So it takes seconds to just take all the data for the entire week and then just merge it into a single frame, and then through a few commands it also resamples it so it can set everything to be 1 second. So now you have a file that's got all your variables and it has the state of everything every 1 second, which makes the analysis very easy. So, as I said, we were able to get rid of the SQLite database for the analysis, so now we just read individual data tables and then we merge them all, and we can also visualize. It's got there's this package called digraphs, which creates interactive JavaScript-based charts, and it makes it easy to, R makes it easy to take that data and create these charts. And once the charts are created, you can actually zoom in time space and look at just that moment, just that hour, just those few minutes, or you can expand out your time window and look at the whole day worth of data. And we also, because we're collecting GPS data, we also created maps out of the data that came out. So what we end up with are these files that show for each day data elements combined together. So on the top there, you got a line chart that shows the speed according to the vehicle, the speed according to the GPS data that we have, and then little squares with the number of the picture. And when you click on a picture, actually just hover on the picture, then the picture appears on the right. This is running on the browser. And then below it, we have state variables like, is the seat belt on or off, or what's the position of the ignition. So you can synchronize all these displays so that when you change the time window that you're looking at one, it updates the other one and makes exploring the data much easier. So that's just a zoom-in version of that chart. And then just a GPS trace color by speed from that, for one of the instrumented vehicles. Okay. So the bottom line is, we always felt very strongly from the beginning that when recording the data, you should try to keep the original resolution. So if you want to go back and look at it at finer time resolutions, like every half a second or every tenth of a second in some specific event, you can still do that. It makes the logging in the application that's doing the data acquisition very simple. It just takes the data as it comes and records it. But the challenge is we were trying to use the tools that we knew, SQL, to merge the data, and that just wasn't working right. So it's a good idea to go look at other fields of research. These packages, they had already been developed for other types of problems, for dealing with other types of instrumentation. So you just have to explore outside your comfort bubble, I guess, and try to find other problems that are similar to yours that other people may have already solved. And like the digraphs and the packages in R that I talked about. And because we were able to do it all in R, that also made the batching of the data extraction process much easier. So we're in Atlanta, we're developing the software that runs in the instruments. We're also developing the tools that are used to extract the data and process it out. But we don't want to be running every single file for the people that are actually instrumenting these vehicles, and they're collecting data every other week basically on these vehicles. So if they can run it themselves, that makes it easier for us, and that also allows them to not have to wait for us to look at the data. So as soon as the data comes back, they can download it into a laptop, and the laptop has R installed on it. They run through it, they get the data out, and there's no need to have a server to support any of this functionality. And that's all. Thank you.